now we're going to use our circuit elements to rethink about the body fat circuits. But we're going to draw them as elements. And we're going to go over those Kirchhoff rules here. So let's see, the circuit was basically, it was like putting a battery with an EMF across your arm or your legs or whatever. And it thought about your fat and muscle in parallel, is what we would call it. So it looks something like this. It had a battery. So now we're going to draw the battery on the left. That's what I like to do. That's just how I roll there. And that's going to come down to your arm, where part of your arm is there and part of your arm is there, like that. So this is the resistance of the muscle part of your arm, and this is the resistance of the fat part of your arm. So this is that part where we said, okay, it's like a cylinder. Your arm is like a cylinder, and it's part fat and part muscle, like that. So we said the current splits to go in these two regions and then comes back together. So that's what we call in parallel. When the circuit splits, or when the current has to split and go one way or the other, that's a parallel circuit. The rule we want to point out for this one is, I'm going to say K's, because I don't want to keep writing Kirchhoff, Kirchhoff, his junction rule. So when you're analyzing circuits, you look for places where there's a junction where the current splits, like here and here. And the rule is simply, I think we probably said something like this before, is that the current has to add up. Current is conserved, charge is conserved, so however much current goes in also has to come out. So here, if we have the current, some goes here, goes through the fat, some goes here, goes through the muscle, and this is I total, IT, is what flows in, then in has to equal out. Okay? So the current total is the current due to fat plus the current due to the muscle. Or the current in the fat and the current in the muscle. That's basically Kirchhoff's junction rule. You can apply it here and you can apply it here. You're going to get essentially the same equation. If we get into real big complex networks of equations, this becomes useful to apply in different places. In a simple equation like this, it's not telling you anything different here and here. Okay. We could look at another body circuit and say, let's see, this is one I didn't make a video for. Maybe I will and go back, and then you'll never know. It's just revealed that I didn't. And it is the holding hands. I had one board on what would happen if two people tried to trick the body fat measuring device. Instead of just holding both parts, one held one, and then they held hands, and the other held the other. What would the reading do? Let's see, so that will look something like this, the battery, and then here's one person holding it, and they're holding hands, and there's the other person. So R1, R2, hold hands would be like here, hold device would be there, and hold device would be there, if you see what I mean. Right? So I'm holding one end of the device, and I'm holding this person's hand, and we're holding hands, and it goes around. And the current would go through all the way through both those. What would that do to the reading? That was the question. And here, when I say R1 and R2, I mean sort of the equivalent resistance of our entire arm. We're not dividing it into fat and muscle here, although we could. We could break each of these into a parallel branch. We'll do that later. Okay, so but all we want to take from this really is the other K rule, Kirchhoff's loop rule. It's what we kind of intuitively figured out earlier, is that the sum of all the delta of voltage drops has to be 0. Now you say, what? That doesn't sound right, because we just had them equal or something, that the EMF equals what? But if you do it real carefully, you find that the signs will work out that they do sum to 0. So what you do is you imagine you're a little charge carrier, a little positive charge carrier, and you make a loop around the circuit, and you imagine how would the potential change. And that tells you if you make them positive or negative. So let's go around this circuit. Here we go. Here you are at 0 volts, and here you are at EMF volts. So I'm a little positive charge carrier. I go from 0 to plus EMF. So what is the potential difference for this first piece? It's E, the EMF. EMF volts minus 0. So this would be plus the EMF. So then it cruises along, the potential doesn't drop through a wire because its resistance is 0, etc., etc. And then there's a delta V1, a voltage drop 1 across R1, V equals IR. And is it going to be positive or negative? Well, you're going from a high potential to a low potential, so it's going to be negative. So that would be minus delta V1. If we say the value delta V1 is an amplitude, we'll put the negative in. And then you go from here to here, potential is also going down, right? Potential always goes down for a resistor as current flows through it. You're always losing potential to heat and to dissipation. So that's minus delta V2, minus the voltage drop across 2. And then you can see it is the answer we got before. Take these two negative values to this side, and you get that the EMF is delta V1 plus delta V2, the sum of the two voltage drops. This is just the formal way to state it. It's really just the intuitive thing. Whatever voltage is applied here gets dropped here and here, and it has to add up.